Right. At this stage, we could want to have a look further into the behavior of the AG25 foil. So let's keep only its polars on the graphs. And if we switch to 2-graph view by pressing T on the keyboard, we can see that something occurs, for instance, at 5 degrees AOA between the 20,000 Reynolds number curve and the one for 30,000. There seems to be a sharp drop in performance in lift coefficient and perhaps also in drag coefficient. So let's change our variables. Here we'll keep lift versus AOA, and here we'll switch to drag versus AOA. Okay? And indeed, it seems that at a certain Reynolds number we have some change of behavior. And usually this is called the critical Reynolds number. Below we'll have laminar behavior. Above we will have turbulent behavior. And there is a way to investigate this using XFoil. This is by using the type 4 polar, which is specially meant for this kind of investigation. So let's type a type 4, let's enter a type 4 polar. We'll set the forced transitions at the trailing edge, which is specified by 1 here. This is the coordinate on the trailing edge, both on the top and bottom surfaces, and we'll leave the transition criterion, the automatic transition criterion, to what it was at 9. Okay, and let's run this analysis from 10,000 to 100,000 RPM. Okay, now we do have a new curve which has come up, it's here. But of course, because we ran it at a fixed AOA of 5 degrees, it's a vertical line in these plots here. So what we'll do is we'll hide all the polars, just keep this one in the plots, and change the X variable to Reynolds number on both graphs. Now that we see that at 5 degrees the lift coefficient changes significantly between 40,000 and 20,000, so our critical Reynolds number is somewhere in between. And if we want good behavior, we will probably want to operate in this range here. Same, the drag coefficient drops sharply at 40,000 Reynolds number. Okay, let's save this for now and try to run a new investigation, but see what happens if we set the transition criterion or the force transition at roughly 1/3 of the chord, both on the top and bottom surfaces. And I'll change the name here, force transitions, otherwise it will overwrite the previous type 4 polar. Okay, and we run the analysis again. Okay, the random color is not well suited, so let's change that. Now we can see that with forced transitions we've changed the behavior significantly, and we have good lift properties at lower Reynolds number, and also we have reduced drags at lower Reynolds number. What did we do? Well, essentially we forced the transition from laminar to turbulent behavior upstream on both the top and bottom surfaces, and this improves the behavior. For instance, or for example rather, it's the same reason why we have dimples on the golf balls, is to force this transition. If ever you have the opportunity to strike a totally smooth golf ball, as I have, you will see that the range is about half as what it is when you have dimples, and this is this effect here. Okay, so in such a case, for instance, if you want to operate your foil at 5 degrees AOA when it's on the airplane, you'll have to fly it at least 40,000 Reynolds number to have good performance.